Thank you, everyone. So today I'll be talking about a counterintuitive idea how adding noise to data can actually make models better. So this talk is based on the experiments that I was running over the past few weeks over clean training, structured noise, unstructured noise, and their effects on robustness. So today is not just about looking at the graphs, it's more about dissecting the mechanics of failure. So we are going to be breaking down how exactly information loss, then we will be going over our experiments on Cipher 10 to answer a specific question. If I train a model on a unstructured noise, does it get better at structured noise as well? And the reality is that it's more complicated than just a simple yes or no question. So the idea is that the all noise is not created equal. We categorize noise in basically two families. We have our structured noise, which is the most common form of natural noise, which is what you would primarily observe if you're clicking through a blurry camera. And unstructured noise is typically found in data corruptions for more specificity, such as when you're saving a photo and the photo does not entirely get saved. So that is an example of unstructured noise. To understand robustness, we have to understand how these corruptions exactly work. So on to the structured noise. So before we dive into structured noise, we'll kind of go around Gaussian distribution or normal distribution. A key property of Gaussian distribution is that small deviations are very likely and large deviations are increasingly unlikely. And more samples are close to zero, but occasionally the model will see a stronger perturbations. That's what makes Gaussian noise a strong model for real-world uncertainty, such as when you have sensor noise, measurement errors, numerical errors, and where extreme errors are rare, but they're not impossible. So in this case, what you'll have to observe is that for all our experiments, the mean is around zero, and the variance is around, mostly when we are training is around zero point 0.2, and when we are testing, it varies by testing parameters. So now on to the Gaussian noise. So Gaussian noise is additive. In this case, we sample a value from normal distribution, the bell curve, and we simply add it to the pixel. So this mimics thermal sensor noise or low light ISO gain. Now you can see at 25% the image is blurry, but you can still see the pattern of how it looks like. But when you get to 75%, the entire texture of image is gone. Now this slide is purely illustrative. I'm not changing how Gaussian noise works, but the idea is that I'm zooming in on a specific region of an image made up of 4 independent pixels. So in this case, the idea is that each pixel receives their own independent noise sample, and that noise sample changes based on the sample noise value. So this independent pixel-wise operation is applied across the entire image in real experiments, and this example is simply a visualization aid, not a different noise method. So Gaussian noise adds small perturbations to every pixel, which means the input becomes slightly different every time the model sees it. So what this does internally is force the neural network to stop over relying on one tiny pattern when we are training it with Gaussian noise. But what happens is that the model has to average over local neighborhoods because high frequency jitter gets washed out if the model tries to rely on the finer details. So Gaussian noise is essentially acts like a regularizer. It smooths out the decision boundary, reduces the model sensitivity to small perturbations, and encourages more stable features. Models trained with Gaussian noise tend to generalize better because the network learns to focus more on the broader structure instead of brittle pixel level details. Now, speckle noise is very similar to Gaussian noise, but the idea is that the sample noise value is basically multiplied, not added. So what that basically means is that the brighter pixels would, in theory, get noisier, whereas the darker pixels would stay clean. And this is more commonly found in radar, medical imaging, and laser sensing. Now, this is very mathematically hard to filter because you cannot just subtract a constant mean, but the noise is tied to the signal itself. So the same example as what we did with Gaussian noise, but Let's assume that we have the same image made up of 4 pixels, and we are doing the same pixel-wise operation to speckle noise. Now, the same thing here is that each pixel will receive its own independent Gaussian noise value, which is why for some the effects will be more, and for the others the effects will be extreme. But the idea is that in a real world image, this operation would apply to all the pixels in the image, and the effect would be varying based on the noise value they receive. So now going back to speckle noise and its difference from Gaussian noise is primarily that the speckle noise is mostly multiplicative. So it amplifies the effect instead of just adding to it. So this creates a non-uniform distortion pattern, and as a result, the model has to learn features that are by definition contrast invariant and intensity robust. And higher intensity regions are unstable under speckle noise, so the model has to find cues that don't depend strictly on brightness or local contrast changes. Now, in a way, speckle noise forces the model to look past the lighting conditions and latch onto deeper structural patterns. Now, onto the unstructured noise. Now, pixel shuffle, now as the name implies, what it does is that it takes a specific set of pixels and teleports them to different locations in the image. Now, the main idea is that this is mostly happens in data saving errors, where parts of the picture might be incorrectly saved, so we might have missing elements there. Now at 25%, you can still kind of identify what's going on, but at 75%, the image is almost gone. And the idea and it works very simply. You take pixels from a specific portion of the image and you put it at the other. Now the same toy example, but instead I'm going to say that we are not using the 4 pixels. Instead, let's assume each block has 4 individual pixels. And what we are going to do is apply pixel shuffle. And at the very end, you can see the entire texture is basically gone, is not really close to the original one there. Now you can see that this is very important because pixel shuffle relies and destroys on the very local structure and patterns like edges and shape. So if a model relies too heavily on local features, pixel shuffle will actually hurt it more. But if the model has learned global level features, then it can still survive pixel level noise. So pixel shuffle is intentionally brutal. Now, the main reason CNNs fail on that because CNNs fundamentally depend on the idea that nearby pixels form meaningful patterns, edges, corners, and texture, but pixel shuffle actually breaks that assumption. So under this corruption, a clean trained CNN would actually collapse because its entire inductive bias is violated. But if we trained with unstructured corruption, the model learns to depend more on global or mid-level patterns rather than overly local cues. It becomes less sensitive to small spatial distortion and learns features that tolerate structural disruption. In other words, pixel shuffle teaches the model to see the forest, not the individual trees. Now, finally, in random erasing, now this isn't distortion, but in this case, what we do is that we zero out rectangular blocks in the image, simulating occlusion. Now, this tests object permanence. Now, if a model can only see a part of the image, can it still infer what that particular object is? Now a scenario would be that if we are training a model on specific on recognizing different type of vehicles. Now, could it still recognize what kind of vehicle is it if it just sees the tires? That's what random erasing actually trains it for. Now, this slide again shows how random erasing works at a small scale. Now here we are actually erasing block by block. So initially you can see we start by one, and we eventually get to 3 by 3. Now, as we increase the erasing size, a larger portion of the image is removed, simulating partial occlusion. However, the important part to remember here is that this actually does not corrupt, it actually permanently deletes that particular information from the region. So the main idea is that the model has to rely less on any single local patch and instead learn features that are more distributed across the image. Now, random erasing simulates occlusion by deleting a rectangle part of the image for CNN. This is extremely challenging because critical parts of the object might disappear. But a clean trained CNN would actually fail catastrophically. But if we train it with this, then it can actually learn redundancy. Does it will not rely on one location or one component of the image. Now this mirrors real life scenarios, such as partially covered cameras, shadow blocking sensors, or video frames with incomplete sections. Now, in this case, the main idea to note is that the model has to learn to infer from partial information, and that has to become more robust to partial observation. Now, on to the experiments. So we did three experiments here. We have our experiment one where we measured the fragility of a clean CNN. We exposed the baseline to different input corruptions and observed how rapidly the performance dropped. So that gave us a reference for all our comparisons. Now, experiment two injects Gaussian noise directly into the feature space. And that let us evaluate how disturbing internal activations actually influences robustness without altering training data. And finally, on experiment three, we focused on input level noise augmentation. Here, what we're doing is that we're adding noise to the input itself and testing which produces the strongest improvements against noise at test time. So before comparing the noise strategy, we fixed everything the same. We have the same cipher 10 data set, small CNN, same optimizer, same number of epochs. I I use the same cipher 10 test set from severity levels from 0 to 1. And for each severity level and corruption time, we ran 100 evaluation passes and reported mean accuracy. So the curves you see are directly comparable, only the training noise changes. Now onto the experiment one. So in the first experiment, I corrupted internal features, not the input image. I defined a feature Gaussian noise module, which basically added Gaussian noise to the features, and then we plugged this at three different places. At test time, these noise modules are inactive, so the inference is deterministic. And then this was compared against a clean baseline that has the exact same architecture but no noise in the feature space. So before we dive any further, I think it's important to understand how the feature noise would actually work. To build some intuition, let's focus on this. Now, the exact architecture here is not important. The point is that in a standard network, each neuron computes a deterministic function of its inputs. If the same image comes in twice, then you would get the exact same activation, such as N1, N2, all the way to N8 every single time. Now, under this setup, a model can become very fragile. It might rely heavily on one neuron being exactly the right value. But if a neuron gets perturbed by noise at test time because of corruption in the image or numerical noise, the prediction can flip completely. Now, let's keep this clean image in mind and let's see what happens when we deliberately inject noise in training. Now, here's what feature space noise training looks like conceptually. Instead of feeding the new layer the raw activations N1, N2, all the way through N8, we actually add a Gaussian noise term ZI, so N1 plus Z1, N2 plus Z3, and you get the idea. Same thing for layer 2. So you can think of Z as a small random bump drawn from Gaussian with mean 0 and standard deviation of zero point 0.2. Every training step, the network sees a slightly different internal representation of the same image. Now the effect is very similar to dropout, but instead of turning neurons on and off, the model base consistently being asked, would the prediction still be correct if the features were a bit noisy? Now the main thing here is that the network learns decision boundaries that are stable to these internal jitters. But in nutshell, the network learns to separate the signal from noise and get better at noise itself when we evaluate in testing. So when we evaluated both models, we can see at Gaussian noise, we can see that the clean accuracy starts at 57% for both. As we increase the noise severity, for clean baseline drops very quickly, but the feature noise model goes at around 53%. Now this gap persists and it often grows as we go to higher noise levels. With speckle noise, which is multiplicative noise, we see a similar trend. The feature noise model is consistently outperforms the baseline, almost all non-zero severity levels. Now, the main thing to notice here is that uh, for each severity type, this is the mean, and it was tested at 100 evaluations per severity level. So the main takeaway is that injecting noise to internal features actually improves robustness to additive input noise without changing the test time architecture. Now on to the experiment two. Now the second experiment is classic data augmentation with noisy inputs. Instead of fixing the internal features, I corrupt the input image during training with standard deviation of uh, zero point 0.2. Again, the architecture and optimizer is identical. The only thing changing is is the is the training data. One model sees the clean Cipher10, the other one sees the noisy Cipher10. And at test time, both models are evaluated on the same suite of corruptions. We have one Gaussian noise, speckle noise across the full severity range. Now, training on noisy inputs actually trades clean accuracy for a big gain in robustness. On clean zipper 10, uh, the model reaches at about 58 to 59, whereas the model trained with input noise actually reaches at 54. So if you care about perfect clean data, the baseline is slightly better. But as soon as we add Gaussian noise at test time, the story flips. At very high severity, the clean model drops to 15% accuracy, whereas the input model is performing at 28%. Now, speckle noise shows the same pattern. The noise trained model actually loses less accuracy as the corruption increases. Now, this experiment supports the idea that structured data corruption during training acts like as a robustness regularization. Now, on to experiment three. Now, in the third experiment, I wanted to go beyond the simple additive and multiplicative noise and try unstructured localized corruptions. So, in this case, we are doing two transformations. We are doing a random pixel shuffle and a random erasing wrapper. So, in random pixel shuffle is basically we are saying pick a fraction of all pixels and randomly permute their position. So, this breaks the local structure, texture, and edges without changing the global color statistics. But in random erasing wrapper, what we're doing is that we're erasing random blocks in the image similar to occlusion, and the erased area size is controlled by a severity parameter. Now, during training, the net unstructured noise model applies these corruptions on the fly, but only in the training mode. And again, the baseline is trained on the clean data as before. So when we evaluate this on structured corruptions, the clean model actually does better. The unstructured noise was actually not trained to handle this type of corruption, so robustness there is limited. However, when we test it on pixel shuffle and random erasing, the advantage flips. As more pixels are shuffled, the clean model accuracy falls sharply, while the unstructured noise model drops more slowly and keeps a clear margin. For random erasing, the clean model is stuck at around 26% accuracy, but the unstructured model is at about 35 to 36%. So this shows that the robustness is highly task specific. Training on one family of corruptions helps mostly for that family or closely related ones. So now back to our question, can, if we train a model on unstructured noise, can it perform better on structured noise as well? Now it comes down to conflicting lessons. Gaussian training actually teaches the model to trust local neighbors and smooth them out. But unstructured training teaches the model that neighbors are essentially liars. They might be shuffled or erased, so it learns to ignore them. So the result is you cannot smooth out what you have learned to ignore, but the model eventually learns based on the family of corruptions that it's trained on. So that's it. I'm open for questions now.
Do you see any effects on the distribution of the weights, with dropout or other kind of traditional regularization?
So I did not do dropout primarily because I wanted to make sure that the parameters are same at all times.
Well, I'm saying like you sometimes see like kind of an L2 regularization of the model weights with dropout because I guess of how it's learning to ignore some things. Did you look at the distribution of the weights with Gaussian noise? Did you observe anything?
Not in this one. I primarily just looked at the accuracies, to be very honest.
When you were, one of the graphs you showed midway through, it looked like your two benchmarks reconverged under the Gaussian testing as the severity increased. Do you have thoughts on that? It looked like there was a delta for a bit, but then as the severity increased, it actually reconverged.
So was it experiment 2 or experiment 2?
I think it was experiment 1.
Experiment 1. Yes, that's the main idea is that at level 1 is basically that nothing is visible in the image. So the most explanation was for that was the model is randomly guessing at that point. So that's why you see an identical performance at severity 1. Severity 1 basically means that is not remotely close to what the image looks like.
How did you choose the scale, the standard deviation for the Gaussian noise you put in?
So basically, in terms of coding, I basically sample the noise out of a distribution with that variance. But the main thing to notice here is that if I say I need a variation of, let's just say 0.2, right? That basically means that most of the values will be very close to it, but occasionally you would see a number like 0.4 or 0.1. It really just depends on when you're sampling.
Right.
If it's totally random, that's the main idea here.
Any other questions? All right, let's give Aayush one last round of applause.